Well, good morning and welcome to A Matter Mystery, The Big Bang. This is our first science talk of the week. We're very excited today to be joined by Sanford Lab's experiment support scientist, Mark Hanhardt, who works with the Casper experiment and is also a PhD candidate at the South Dakota School of Mines and Technology. Now, Mark is going to be talking with science comedian Brian Malow about what happened during the Big Bang and how it helped form the early universe and everything else that exists, including us. Throughout the talk, you can submit your questions by Cameo or YouTube or Facebook. Enjoy the talk.
Excellent. So thank you, Constance. Hey, Mark, how are you doing?
Hi, Brian. I'm doing well. How are you?
Good to see you. Mark and I met recently, but we met here on Zoom, actually. We haven't met in person. When we planned this event before the pandemic, I was supposed to, I'm so sad that I don't get to visit the Sanford Underground Lab, but maybe someday. But, you know, one of the weird consequences of a global pandemic is the annual Neutrino Day expanded to become a week of events online. So that's why we're here. And I'll be doing interviews all week at this same time slot, Tuesday through Friday, performing on Saturday. But through the course of the week, I'll be speaking to a variety of physicists about neutrinos, dark matter, the end of the universe, but we're starting today with the beginning of the universe, the Big Bang. And I'm talking to a variety of types of physicists. And Mark, you've actually transitioned from one kind to another. So you're not an astrophysicist, are you? What are you?
Well,
what do you identify as?
Right now, I identify as a nuclear astrophysicist. I study the nuclear reactions that take place inside the stars and make the universe tick.
Excellent. But that's not where you started off?
No, I actually started in solid state and computational physics and then made the switch to dark matter physics. And over time, ended up back in nuclear astrophysics, which is what really gave me the passion to study physics when I was a kid.
Excellent. Yeah. So speaking of when you were a kid, you grew up only 12 miles from the lab where you now work?
Yeah, I grew up in Sturgis, South Dakota, and my father was a hard rock miner here at the Home State Gold Mine. And you know, I thought that's great, but I don't want to work in a mine for a living. I want to study the stars. And
kind of the polar opposite, right?
Right. Yeah, I couldn't think of anything further away. But as it turns out, one of the best places to study the stars is underground. So I find myself walking the same drifts that my dad did.
Yeah. So you tried to get as far away. Here he is. How deep is the mine? Where the lab is in particular. So for people that don't know, well, maybe you could answer this. Can you tell me what is Sanford Lab? Let's just insert this here before you answer that question. So, and how, where is it situated?
Well, Sanford Lab is in the former Home State Gold Mine in Leeds, South Dakota. It is 8,000 feet deep, but the deepest occupied level is 5,000 feet deep. And the level that has most of the big physics experiments on it is the 4850 level, 4,850 feet below the surface of the Earth, which is nearly a mile.
And the part that, so that's just about a mile. And the stuff that you said is deeper, that's not part of the facility, that's part of the mine, the mine?
It's part of the old mine. Right now, It's not occupied by anyone. It's mostly filled with water, though we do have some active work going on at the 5,000 foot level, which is not underwater, preparing for future experiments. And I think we have some geology stuff that's being investigated on the 5,000 foot level.
And let me ask you this, because I actually had the opportunity to visit another neutrino detector in Sudbury, Ontario, Snow Lab, and that's about that deep, maybe a little deeper underground in an active nickel mine as opposed to a former gold mine. And beneath the lab, so is it the same sort of detector? Because beneath the lab facility where everyone works is this vast spherical chamber, and it's filled with heavy water, and that's the kind of detector. Is it the same kind of detector that Snow Lab has?
Well, the detector that we're going to install in the future at Sanford Lab, that is a neutrino detector, it's aiming for the same goals as that project, but it's a vastly different type of detector. Rather than a giant sphere, and I know the sphere you're talking about filled with heavy water, different from that, we're going to be using 13 million gallons of liquid argon. So it'll be a much bigger detector volume, much bigger caverns in order to detect our neutrino signal.
And maybe you could just say, so how that's supposed to work. Why do you have a vast chamber of either heavy water or liquid argon? What's the point of it? There's so many questions to ask you here, but how are we going about? So neutrinos are very hard to detect.
And that's exactly it. They are so incredibly hard to detect that if you wanted even a 50% chance of catching one neutrino, you'd have to build a detector made out of lead that was a light year thick. So they interact with normal matter so incredibly infrequently, your best chance of catching one is to just gather a whole bunch of mass in one area and let the neutrinos interact with that entire volume. The sphere in Sudbury that you're talking about is a whole heck of a lot of heavy water. The LBNF dune detector that we will have underground here at Sanford Lab is a heck of a lot more liquid. The idea is that by increasing the mass of our detector, we increase our chances of actually getting one of those neutrinos, because when a neutrino passes through a particle, there's a 1 in a trillion chance it'll actually, interact with anything in a way that we can see. So we increase our odds by increasing our atoms.
Can you tell me what is it? What's the nature of that interaction? Like why heavy water? Why liquid argon? And what does happen that makes it possible to detect a neutrino?
Well, the details are really mathematical in nature, but the quick version is it's a weak nuclear interaction that neutrino passes through the nucleus of the atom of whatever you're using, and it exchanges what we call a boson that creates a tiny change in the particles inside that atom, and that change in whatever material we tend to use creates a tiny flash of light that we can pick up with instrumentation. And the reason we use heavy water, or the reason we use argon, is that we know in those particular materials, they make a distinct flash when we have that particular weak nuclear interaction. And they also are incredibly low in backgrounds that would cause other flashes that would be confusing.
Okay, and in fact, that's the whole reason these neutrino detectors are so deep underground, right? Can you explain that?
That's exactly it. On the surface world here, we are bombarded with cosmic rays and cell phone signals and radio signals all the time. And when you build an incredibly sensitive detector, you're going to be picking up all of that. It's like building a microphone that's designed to listen for, say, a cricket, and then putting it in the middle of a football stadium with a crowd, shouting crowd. It's going to pick up too much. So you need to take it and the cricket somewhere that's incredibly quiet. And that's what we find underground. We're able to block out all of the signals, all of the cosmic rays, or most of them anyway, so that when we turn our detector, we're not, flooded with the noise of other signals. We're just getting the signal we're looking for.
Yeah, so back where I think we diverge, you were saying, it's like that really surprising result that you want to study the stars, so you, instead of going to a mountaintop with a telescope that peers through even less atmosphere than at the surface, you're going a mile underground to better perceive the distant universe. But that's really just to block out everything else, and you're not going to do visible light astronomy underground, and you're not going to do anything else, like, right, like X-ray or
Yeah, that's absolutely right. But it's an irony that a mile underground with a mile of rock overhead, you have an incredibly clear view of the stars, at least within the accelerator that we use on the Casper project. The stuff I'm interested in takes place inside the heart of the star, inside the very core. And that's something you can't see with a telescope anyway, because there's a lot of other layers of the star blocking that. So underground, we're able to recreate the conditions inside the star. We're able to recreate the heart of that star and watch those reactions play out in this, elegant silence that we are afforded underground.
That is fast. So, so this facility, the neutrino detector, when is that being built and expected to be finished?
I don't know off the top of my head. I think it's 2024, 2025.
Okay.
And we expect to have, am I too soon, Connie?
No, I'm not sure what the date is. Their pre-excavation is going on right now, and so that'll have to happen first. They'll have to have all of that completed. And there's work to do before they could even start digging underground or excavating the caverns on the 4850 level.
It's years out anyway.
And then does oh, I see. Does so since that facility hasn't been built yet, what's going on at the lab now? Are there other experiments that have been going on? And when you describe that it's recreating what's happening, I'm trying to understand what you said about understanding what's happening inside the heart of the star. How is that recreated at the Sanford Lab?
Well, with the Casper experiment, which stands for the Compact Accelerator System for performing astrophysical research, what we've done is we've built a small accelerator underground, and we use that accelerator to basically shoot particles at a target, and when those particles hit the target, they undergo nuclear fusion. And that nuclear fusion is the process happening inside the heart of a star that we're watching. So when that fusion happens, we get some energy put out, we get some particles put out, and we're watching very closely those things that come out of the reaction so that we can understand how this actually takes place inside the heart of a star. As for other experiments, there's somewhere between 24 and 32 active experiments going on underground right now, depending on how you classify active, in fields from physics to biology, chemistry, geology, engineering. We have a lot of active experiments going on underground, and I'm typically more familiar with the physics ones, because that's my field. But we have a lot of exciting stuff going on in the other fields as well.
Oh, really? Like, can you just I know you don't know a lot about it, but you mean outside of physics, there's other experiments?
Oh, yeah. There's active groups looking for what we call extremophiles that survive underground. Extremophiles are types of life that can exist in really extreme environments. For instance, a mile underground where there's no sun, there's no obvious food source. But it turns out there's bacteria and some organisms that live in the rock and are able to feed off of the minerals, and they absorb heat from just the compression of the earth. And it turns out these organisms have developed these really unique abilities for surviving down there, abilities that could be useful for us, abilities that could make them effective antimicrobial material for medical use, or they may break down plastics more effectively than anything we've seen on the surface. They may even be able to create methanol for biofuels at a much greater efficiency than any process we've got right now. These extremophiles are extremely interesting, not just because of what they can do for us, but also because they help us understand how life could form on other planets. If we want to go looking for them, which the NASA astrobiology group definitely does, they try to understand how those extremophiles survive here, what kind of signals or gases or evidence that they exist that they put off, and then we can look in the stars for those sorts of things.
So in all this talk of these experiments and of neutrinos and what's going on in the heart of the star, how do we tie this back to the Big Bang? Is some of this, are neutrinos is the study of neutrinos relevant to our understanding of the Big Bang?
Extremely. In particular, the Majorana demonstrator experiment, which we have on site, and the LBNF Dune experiment that we will have, seek to answer some specific questions that come from our understanding of the Big Bang. In addition to that, the LZ dark matter detector is trying to understand the nature of dark matter, which plays a very big role, again, in the Big Bang. And then my experiment, Casper, is trying to understand what we call stellar nucleosynthesis, which is, to break that down, it means how the atoms that make up the universe were created inside of stars. That's a natural extension of the Big Bang, which provided all of this material for the stars, and then, had to be transmuted into new.
The Big Bang only provided simple hydrogen, a little bit of helium, not much. The Big Bang didn't provide that much.
It didn't provide much in complexity, but it provided all of the material and all of the energy, and it's fantastic to understand the evolution of the universe from the perspective of the Big Bang.
Can you give us a definition of the Big Bang? I mean, not that we haven't heard of it, but if I ask you for a definition of the Big Bang, how would you describe it to a layperson?
Well, a lot of scientists would define it as the event, the single explosive event at the beginning of the universe that created all of the matter, created all of the energy, and allowed us to be here. For me, however, I think I have a bit of a different take on it. I would define the Big Bang as the event that not just started the universe, but the one that is still unfolding now. In my perspective, we're still living through that Big Bang. Everything that happens in the universe right now is a continuation of that Big Bang. And the story of the Big Bang continues until the very end of the universe itself.
So, like the Big Bang, a lot of people, and even the name Big Bang suggests an explosion, but it's not really an explosion. But if we use that analogy for a second, right, I like what you just said, because an explosion isn't just the moment of the ignition, it's the whole thing playing out. And in this case, this not explosion, but this process has been playing out for 14 billion years, right?
And will continue for, we don't know how long.
Yeah. And you know what? On Friday, I'll be interviewing Katie Mack about the end of the universe. Do we know something? We must have some estimates, don't we, for how long, or do we not know enough? If that's the case, do we not have some estimate for how long we have? And if we don't, what's the missing information that we would need?
Well, it depends entirely on which scenario for the end of the universe you follow. The timescale is different for each of them, and I don't want to step on Katie Mack's talk, so I won't discuss much of that. But
can I offer up? Let's say we're talking about the heat death of the universe, for instance. That it's going to continue to expand and expand. Yeah. Maybe you can explain it a little better, and then and it all sort of levels out, right? Everything sort of.
When you're talking the heat death of the universe, the numbers get ridiculously large, and unfortunately the uncertainties get ridiculously large as well. So we're talking trillions upon trillions upon trillions of years before anything even remotely interesting regarding the heat death happens. It's hard to describe exactly how far out a heat death scenario would take us.
So I shouldn't be that anxious about it.
It's not something that should keep you up at night, no.
And who is let me ask, who is handling the chat questions, so I just have a name to put with that? Or does it matter? Like, I saw someone for a second.
Aaron will be handling.
Karen. Okay, thanks, Karen. Okay, that's good. We have some questions coming in, and I'll go to them soon.
Oh, I'm sorry.
Right.
That was a question that just got asked.
Right. Let's. Oh, you know what? That's really weird because I just saw that if you're familiar with Randall Munroe and his cartoon XKCD, I just saw that today in the New York Times, he actually has a piece that's about this very question. I think I didn't get a chance to read it yet, but this seems like a variation on it. If you had enough neutrinos packed together into a ball, would you be able to see them with the naked eye or a microscope?
Oh, that's a fantastic question. No. uh, the, the reason we can't see neutrinos is that they don't interact with what we call the electromagnetic field. Everything that we see is a result of photons, right? The reason I can see the sun is it emits photons. The reason I can see the computer screen is that the LCD screen or LED screen emits photons. The reason I can see Connie is that photons reflect off of her and hit my eyes. Those photons are a manifestation of this electromagnetic field. Neutrinos don't interact with that field at all, so they can't produce photons, they can't reflect photons. Photons pass right through them, so they can't be seen in any way. Now, if you were to get a whole bunch of neutrinos somehow packed into a really dense sphere, it's possible there are some sort of reactions going on there that would, some weak nuclear interactions that would create some sort of signal that would then itself interact with the electromagnetic field, but the neutrinos themselves you could never see. If you can see,
and is that what you're saying? That when you do detect them, it's not because of the neutrino interacting with the electromagnetic field. It's because the neutrino interacts with another, with what?
With something else. In the case of,
and then that has does interact with the electromagnetic field.
Right. So we're seeing a secondary response from that neutrino. So we never see a neutrino directly. If you saw a neutrino, it would cease to be a neutrino because it's interacting with the electromagnetic field, and that's something neutrinos don't do.
So also that question, the idea of taking a bunch of neutrinos and making them into a ball, so that made me think, so photons are always moving, but some particles like protons aren't always moving, and we have accelerators to accelerate them, so they can be maybe close to stationary. I guess nothing in the universe is completely stationary, but they can be basically not moving or accelerated to close to the speed of light. What are neutrinos like? Are they more like a particle like that, or a photon that's always moving? I understand that neutrinos move very close to the speed of light, but is that it? Do they just have one speed, or tell me something about that?
I'm not actually sure. I do know that neutrinos do travel very close to the speed of light, the ones that we interact with, but I think that may be because of the energy that they're given when they're created.
Okay.
As far as the quantum mechanics I know off the top of my head, I don't think there's anything to stop a neutrino from not moving at all. I think we could stop one from moving, but I could be wrong on that. I'm afraid that's not my field of expertise, but the quantum I know tells me it has a mass, it could be stopped.
Well, I believe my interview tomorrow morning is about neutrinos. So let's bring it back to the Big Bang. And you said a little earlier that there were some specific questions that the research going on at the Sanford Lab attempts to address some specific questions related to the Big Bang. Can you tell me something about those questions?
Yeah. Well, I suppose the first one that makes sense is the work being done by the Majorana Demonstrator Project and will be done by the LBNF Dune Project, and that is specifically trying to answer, why is there matter in the universe? So the way we understand the Big Bang, we had this, like you said, it wasn't so much an explosion, but what we had was this rapid expansion of all of space-time at once. From this spot that was infinitely dense, infinitely hot, infinitely energetic, that spread out into the universe we know now. And as it spread out at one of the very early stages, a lot of matter was created in a very small space, as well as an equal amount of antimatter. Now, if you know anything about matter and antimatter, when they meet, when they come together, they annihilate. They turn into pure energy with no matter left over. So if we had all of this matter created and all of this antimatter created in a small space, it should have all annihilated. There should have been no matter left over for the universe to create galaxies and planets and stars and you and me. But obviously it did. So
Are we kidding ourselves? Maybe there really isn't a universe. Maybe we're not here.
There are theories out there, but sticking to the Big Bang,
Yeah.
the idea is, how do we explain that all of this matter was created, all of this antimatter was created, because you know that had to have happened? Why is there
it
still some matter
possible
left over?
when they were created, couldn't it have been like the matter went this way and the antimatter went the other way?
That's a theory that's been investigated. So the idea is that, you know, maybe the part of the universe we live in now is made out of matter, and somewhere out there, there's going to be a lot of antimatter, you know, stars made out of antimatter, anti-stars, if you will, and anti-galaxies and anti-planets. But that just doesn't hold up to investigation. As we look out in space, we don't see any of the telltale signs that we should see from that sort of universe. And the math for creating a universe just doesn't work out that way. What's more likely, and what we're investigating in these experiments underground, is that when we had all of this matter created and we had all of this antimatter created, they annihilated in such a way that some quantum mechanical asymmetry set itself up so that 1/billionth of the matter was left over and all of the antimatter disappeared. So that 1/billionth of all the matter that was created at that moment would explain all the galaxies, all the stars, all the everything, all the matter in the universe was this 1/billionth that was left over. And that can only happen if it turns out that neutrinos, these particles we've been talking about, are their own antiparticles, something we call a Majorana fermion. And that's what the Majorana demonstrator project is looking for, and that's one of the goals that the LBNF Dune experiment is looking for, to see if neutrinos can be shown to be their own antiparticles. Because if they are, we have an explanation for why the matter's here. If they aren't, we've got some work to do.
Interesting. I always like this thing about scientists too, that it's a little different from most people when a theory, like the standard model of particle physics, if there's a flaw in it, to most people that would be horrible. Our precious model that should explain everything is flawed. But to scientists, sometimes it's like, that's awesome, because if it's perfect, then we have to find something else to work on. But if there's a flaw, then we know that right? I just think that's a great quality about scientists.
It's fascinating. It means that we don't understand the universe in the way we thought we did, and there are new puzzles to be solved. The only thing in physics better than being right is finding out that you were wrong.
Interesting. Do you mind if I ask you questions that you can't possibly answer?
Shoot.
So the Big Bang, I mean, there's so many. I mean, what it all comes down to really is, why is there something instead of nothing? You said every part of this makes no sense to the human mind, that an infinitely small and infinitely hot and infinitely high energy, or maybe, I don't know if it's infinite high energy, but right, I mean, every part of that makes no sense. But you know, what was before the Big Bang, and where did all this stuff come? Because you look and you go, it's quite a lot of stuff. I mean, just the Earth is a lot of stuff. The sun is 1,000,000 times more voluminous. And then you've got a couple 100 billion stars in a galaxy and billions or trillions of galaxies. So where did all this stuff come from? Mark?
You're right. I can't answer it.
But do you think about this? I know that a lot of times sometimes scientists don't like to address questions that they're almost outside the realm of science. You can't address them even. But what do you do with questions like this that are hard to address, like before time, before the Big Bang?
Well, you know,
how do you think about that stuff?
physics doesn't have yet the tools to explain some of these things, but it does give us the scientific method that allows us to think about it in a way that is analytical, in a way that is critical, so that we can try to make some sense out of that sort of thing. So even though we don't have the specific tools that we need, so yeah, I constantly think about that sort of thing. And there are a lot of people who have taken a stab at, answering that sort of question. String theory in particular has a really strong subfield in it that is designed to explain specifically the origin of the Big Bang. Where did all of this energy come from? So there are ways to think about it, even if the tools don't yet exist. And yeah, studying those methods of physics to really get a good idea of how to properly apply that to these questions. And sometimes you end up in this unique situation where you find out the questions you were asking aren't the right questions. For instance, one that I get asked a lot is, what was there before the Big Bang? What happened before that? And it turns out that it's a fantastic question. It's a deep and meaningful question as far as guiding our thoughts. But when you get to the point of actually answering it, you realize the question itself is flawed. Because in most models of the Big Bang, including the one we're talking about here, that was the beginning of time. That's when space-time was birthed into reality. And so there was no time before that. Stephen Hawking described it like this: imagine being where you are on Earth right now and wondering what it's like slightly to the north of you. Now, for us in Leeds, South Dakota, that's Spearfish or Belle Fourche. So I can go up there and I can find out what it's like. And if I want to know what it's like north of there, I can go to North Dakota. And north of there is Canada. But when I go all the way, when I get to the North Pole and I ask, what's it like north of here? That question doesn't make sense anymore, right? There is no north of here. This is where north starts. This is where all the north comes from. And that same question, or that same reasoning, applies to the question of what happened before the Big Bang. When you get to the Big Bang, there's no before then. That's where time starts. There's not a before. And cause and effect break down because cause and effect are, part of time. I know it's a mind warp, and it takes it at you, but when you get really deep into the reasoning of physics, it starts to make sense that, yeah, time is not this infinite thing that we think of in our human lives. It's something that has a definite start point.
It's fascinating that something that every way you look at it, like, how could there be a beginning of the universe, and what came before? And then when you talk about the vastness, like, is space infinite? Well, I can't conceive of infinity. That makes no sense to my mind. But the idea that it's finite, well, that doesn't make any more sense than infinite. Like, neither. And is there another option? Because those are the only two that are obvious to me, and neither one is acceptable. Neither one makes sense to the mind. Finite, infinite, beginnings, ends. What happens after the end of the universe? But aren't there theories about that this Big Bang and our whole universe might just be a small part of a much larger universe?
Absolutely. There are a whole handful of theories that suggest something similar, and the one with which I'm most familiar is string theory, which suggests that our entire reality is just one plane in a whole stack of planes of existence, each one of which is its own reality. And kind of the key concept behind string theory is that these planes have some sort of vibrational qualities that define all of the parameters inside that universe, how physics works and how particles and energy interact. And one of the ideas of M theory, which is the leading string theory candidate, suggests that when two of these planes that happen to be close in whatever ethereal space they are mathematically close in, as they vibrate, when two of them touch, they release a nearly infinite amount of energy that becomes a Big Bang and the creation of a new plane, then a new reality. So in that mathematical framework, Big Bangs are happening all the time.
Mm. So, and then what we think of as the universe and as everything is just everything that's accessible to us, even theoretically. That's
absolutely right.
And as vast as it is, it might be a drop in the bucket for all we know.
Yeah, an infinitesimal part of the universe, just the one we happen to be existing in.
Wow. You're working on your PhD at the South Dakota School of Mines and Technology?
I am, yes.
And what's your PhD in, or what's your thesis project?
Well, my thesis project is specifically understanding the reaction when an alpha particle is shot at a lithium-7 atom. That lithium-7 atom...
I've wondered about this so many times. I can't tell you.
What happens is that lithium atom...
Is an alpha particle a helium nucleus? Or am I confused? What's an alpha particle?
It's two protons and two neutrons,
so it's
which is the helium of a nucleus atom, just with the electrons stripped off.
You said the helium of a nucleus atom.
Oh, yeah.
The nucleus of a helium atom,
right.
Yeah.
That PhD is not going to go well for me, is it?
So it's about alpha particle interacting with what?
Lithium-7.
Lithium-7, of course. So, and why? Why does that? Why are you?
Well, it's.
Well, what would this? Yeah. What do you hope to do with that, Mark?
It ties into. For me, it ties into this really poetic question, which is, how did we get here? After the Big Bang, the universe, like you said before, is filled with a lot of hydrogen and a little bit of helium, and that's a pretty boring universe. So how do we go from that to a universe that contains galaxies and stars and planets, and in particular, me, the most interesting person? And the way it does that is hydrogen clouds out in space over eons collapse under their own gravity until the center of that ball of hydrogen is hot enough to undergo thermonuclear fusion, and a star is born. And as that hydrogen burns and fuses, it turns into helium. And when a star runs out of the hydrogen in the core, it turns that helium then into carbon. And then carbon gets turned into oxygen and nitrogen and silicon and iron, and it creates all these things that are necessary for, say, rocky planets and people. So when some of these high mass stars in the early universe, they've finished creating all of these materials, they explode in a supernova explosion, and they spread the ashes of their cremated bodies out into the universe, which then coalesce into new stars like our sun, and eventually planets where life can form. So the reactions I'm studying in the accelerator underground are some of the reactions along that path. And it's just a way for us to understand our chemical lineage. Where did the atoms that make up my body come from? It turns out they literally come from the 100 million degree burning heart of a star. And understanding each step along that path is really important for us to understand, where is the universe going? How long will stars live? How early could we have had life in the universe? Are we the first ones here, or did we miss the big boom of life? And these are questions that we can only answer by understanding the biggest parts of the universe, the stars and the galaxies, by understanding the smallest parts first, the atoms.
And that was your more detailed explanation of stellar nucleosynthesis. And then, so in a way, his like going back in history, the alchemists and even Isaac Newton pursued alchemy, but they weren't wrong. Transmutation of elements is possible, at least in the heart of a star.
Absolutely.
Or
They
a
weren't doing high
supernova.
enough energy.
Yeah. So Newton probably wasn't going to get there in his lifetime, probably.
Well, no, but he.
Yeah. Fascinating. So did you always know that you wanted to be a scientist?
Yeah. I toyed around with being a rock star, but I decided that I owed it to the world to become a scientist. No, I'm just kidding. Yeah. Since
Are you a musician? Do you play an instrument or?
Oh no, I am tone deaf to a degree that.
Oh, that's so funny. I've actually said this as a joke because I wrote songs with a friend, but I said that we also were kind of torn between being scientists or rock stars. And if you say you wanted to be a rock star, people often go, well, what instrument do you play? And I have to say, I didn't say I wanted to be a musician. I said I wanted to be a rock star. Major difference. So that was all. So that was out of the question. So might as well be a scientist.
Yeah.
Was there anything that hooked you? Yeah. Is there something that hooked you early on?
Well, when I was a kid, I wanted to be, well, like everyone does, a paleontologist. I wanted to study dinosaurs.
Yeah. Dinosaurs.
Yeah. And then eventually I thought marine biologist is the way I'm going to go.
Yeah.
And then in 8th grade or high school, I had a couple of teachers that tried to explore black holes with kids who have the attention span of 8th or 9th grade. So we didn't learn a lot, but it whetted my appetite enough that I could go home and start reading this stuff. And the more I got into black holes and stars and galaxies and the formation of the universe, and in particular what we call the cosmic microwave background, I was hooked. I knew this is what I have to do. And then just after high school, I picked up a book called The Light at the Edge of the Universe, which you and I've talked about, by Michael Limonich. And
you know what? I acquired a copy of that on your recommendation. Yeah.
It's a fantastic book. And it really laid out the cosmic microwave background, and it helped me understand that through really small signals, we can understand a rich story, a tapestry of the universe. And
so, go ahead.
Well, ever since then, I knew this is what I want to do.
Excellent. And, it turns out dinosaurs and marine biology, it's all physics, right?
Absolutely.
Maybe it's complicated. Cosmic microwave background radiation and the Big Bang. Could you tell us about that? What is the cosmic microwave, the CMBR?
So after the Big Bang, we talked about it's this infinitely dense, infinitely hot, infinitely energetic point that expands, and it creates all the matter, all the energy in the universe. As time goes on, it continues expanding and expanding, and about 380,000 years after the Big Bang, the universe is filled with some matter. It's protons and neutrons and some helium nuclei. And a lot of electrons, but there are no atoms because the electrons haven't started orbiting around the nuclei yet.
Is this because it's a too high an energy state?
Exactly.
Yeah. Why it's a plasma? They're not atoms because is it like those everything, like the electrons have too much energy to be contained like that, or
that's
is
exactly
it something like that?
The early universe at that point is so flush with energy that every time an electron starts to get captured by a nucleus, it has enough energy to just escape. And so the universe is made out of this plasma. It's basically glowing with energy, and any photons, any light that is created travels a fraction of a millimeter. And I'm talking like a trillionth of a millimeter before it gets absorbed again. So the entire universe is filled with energy and plasma, but it's basically dark because the photons can't get anywhere. And then at about 300,000 years after the Big Bang, the universe has expanded enough and the energy has spread out enough that the electrons have just the right energy to stop escaping the nuclei. So the very first atoms form, the very first electrons get captured by those nuclei, and we have the birth of the first atoms. And what happens is that those photons that have been created and absorbed almost immediately up to that point are suddenly free to travel in a straight line. They're no longer absorbed by this electron cloud that's absorbing, or that's possessing the entire universe. So we have this light signal that for the first time in the history of the universe escapes. And the universe is this bright light. Over time, the universe continues to expand, and as a result, the wavelength of that light, which is traveling in every direction, from every direction,
It's stretched out because space is stretching out.
exactly, the canvas through which this photon is traveling stretches out, and so the wavelength of the photon itself gets stretched out. And it drops from visible light to infrared light, and then eventually microwave light, which is, on the electromagnetic spectrum, but is not light that is visible to the human eye. And so here we are now, 13.8 billion years after the Big Bang, 13.5 billion years after this moment. And that light is still traveling through the universe from every direction, in every direction, and we can pick it up. Using incredibly sensitive antennae, we can actually pick out this signal. And in fact, if you've ever used an old FM radio or one of the old CRT televisions and tuned to a channel that's all static, about 0.5% of all the static you're seeing is actually that signal coming from space. And that's what struck me. The idea that we have this signal coming from everywhere that tells us a story about the universe. The universe is singing to us in microwave, this symphony that is rich in history. It tells us all about the Big Bang, how we got to where we are, and also how the universe is going to end up. It's rich with this information, and it is, in my mind, it's a symphony.
That is fascinating. And I've described the cosmic microwave background radiation as like a sonogram of the birth of the universe. I really like what you just said. That was really beautiful. And I've always thought it's fascinating. So we evolve on this rock orbiting this star, and there's all this light, and we evolved sensors for it. And then ultimately we discover that not only is light useful for not bumping into things and seeing interesting things, but it's also every direction is all this light of all these different frequencies, all these different wavelengths, and each part of it can potentially tell us different stuff about the universe. I think that's so fascinating.
Oh, absolutely. That entire spectrum is useful for astronomers. And to think for thousands of years, we looked up at the stars and we saw the visible spectrum, and we're pushed to understand the universe on a greater scale, which led us to then, like you said, have these instruments that can pick up. We wouldn't have that without, our ancestors staring up at those stars and wondering why.
Yeah. We have a question from the chat, and you're going to have to tell me, I guess, first of all, it references the Dune experiment and Casper. So before I even ask the question, can you kind of tell, what is Casper?
So Casper is my experiment. That's the compact accelerator system for performing astrophysical research. It's a small accelerator that we use to recreate those nuclear fusion signals that I was talking about earlier.
So the question is, with the huge Dune experiment on the way, will that impact Casper in any way? And what is the future of that experiment? And that's from Serenity.
Well, there's definitely some overlapping territory there. They're going to need to area that's useful for Casper in order to prepare for Dune. So the impact is basically that when Casper is finished with some of their current experiments, we're going to move to a less active mode. We may mothball the accelerator so that the Dune group can carry out their blasting and their excavation without fear of harming us or our experiment. And in that meantime, Casper won't be idle. Our equipment may not be moving, but we're going to be working on a lot of analysis, and we're going to be preparing for the next stage of Casper, which, depending on funding, could involve 2 accelerators shooting particles at each other rather than 1 accelerator shooting particles at a target. So there's a lot of overlap, and there's a lot of we have to play nice with each other because we're in a lot of the same space. But ultimately, I think it's going to work out well between both groups.
The 2 particle accelerators shooting particles at each other, does that just mean that you'll get even higher energies? Because if one accelerator can accelerate a particle to a certain velocity and it can hit a target, but if you do 2, then it's like relative to each other, it's even higher.
That's not so much our concern.
No? It's something else.
Energy is a weird thing in this particular field. We're actually shooting for the lowest energies we can possibly achieve with our accelerator. I see that confused look on your face. That's reasonable because everything we know about accelerators is, the LHC, right, at CERN. They're going for the highest possible energy, but that's because they're trying to recreate the conditions around the Big Bang. That's incredibly energetic compared to the heart of a star, which as far as the universe is concerned is really pretty low energy. So we're specifically going for low energy, which is why we go a mile underground, because low energy interactions are really hard to see with all the cosmic rays hitting us. It's not a problem for LHC and their high energy. So the energy isn't really the concern, but with a dual accelerator set, we change the time at a lithium-7 atom, we can instead shoot 2 heavy ions at each other, say 2 magnesium atoms at each other. And that opens up a whole new set of reactions we can understand. So it's not so much about the energy, it's just different interactions that are also very interesting.
I've heard this, like I always assumed it was like accelerated to shoot particles at targets, but am I right? And I've heard something about that it's not precisely that it's more like you're causing this it's more about the interaction with space-time or the vacuum or something, that it's not actually shooting a particle at a target, but it's like trying to get. Am I expressed? Do you know what I'm talking about?
I think I do. It's not so much something we do at Casper, but the LHC in particular. With their really highly energetic reactions, what they're trying to do is destroy. They're actually able to induce space-time to generate new particles. Really solidly. But basically the idea is that they're trying to induce the space-time to recreate some of the particles that we would have seen around the Big Bang, like the Higgs boson.
Yeah, and the Higgs field, something about causing the Higgs field to kick out a Higgs boson. Exactly. There's a certain, physics can get pretty complex. For those of us who don't do the calculus and just have a layperson's understanding, and you want to understand some of this, sometimes it gets to a level that's pretty deep. I know that you have an interest in STEM outreach. Maybe you could tell me something about that. That's like, why are you interested in outreach? And we're doing it right now. This is an example of your outreach. Why do you do it? Why is that an important part of your work besides just the cool science?
Well, I mean, first of all, I think it's important for people to understand, particularly kids. It's important for them to understand the basics of science and mathematics, so that they can understand, not only the academics, but their world as they grow up. On a more selfish note, though, it's because I legitimately find what I'm doing really interesting, and I want someone to share it with. And curious they are about it, the more I'm able to share this stuff with. And it can be very lonely sometimes working on the stuff that we're working on, because there may be 5 or 6 people on Earth imagine putting in all the work it takes to climb to the top of Everest, and then when you come back down, no one actually understands what it means to stand on the top of Everest. We put in years and years of work to understand, the intricacies of nuclear physics and quantum mechanics, and we're unable to share it, with the people in our lives. So every bit we can do to bridge that gap, to help them understand what it is we do, it makes me feel a little bit less lonely.
That's interesting. Is there something that you wish more people understood about science?
Absolutely. I mean, I could give you a list. If I had to narrow it down to one.
You don't have to narrow it down.
Okay.
But let's start with one.
I think at least what I wish people understood about the field is that this idea of the dispassionate, cold and clinical scientist is unrealistic. The way, physicists in particular are portrayed in movies or TV shows, it's not accurate. There's a lot more art to what we're doing in trying to understand the universe the way we do. For me, this deep level of physics where we're trying to understand the universe itself is more poetry than anything. And I suppose I wish people would understand that, sometimes we're trying to pursue that not because we're robots, but because it fulfills something deep within our souls. This is why we're here, to understand. For me, that'd be the number one thing I want people to understand, at least about the scientists themselves. About science, I wish more people understood that it's real. I feel like we're living in a world where a lot of people are questioning, the reality of science.
Yes, all across this vast flat Earth of ours, people are questioning science.
Yeah, that one in particular really bugs me. But yeah, I wish more people would understand that, science is not just real, but it's the foundation upon which our civilization is built.
Yeah. Is there a question that you most want the answer to?
Ooh, when will I finish my PhD?
We're all asking that one.
No, absolutely. There's
maybe more than, it doesn't have to be one, actually.
This isn't technically my field, but a solution to the quantum gravity problem would.
What is the quantum gravity problem? Okay. What is the quantum gravity problem?
So in the universe that we know, there are 4 different forces that can interact between matter and energy. And those forces are gravity. We're all familiar with that one. There's electromagnetism, which is responsible for light and electricity and magnetism. There's the weak nuclear force, which we talked about. It's responsible for some interactions with neutrinos. And there's the strong nuclear force, which keeps the nuclei of atoms together. we have reasonable mathematical models for uniting electromagnetism and the weak nuclear force. That's not a problem. We have reasonable models for combining the strong nuclear force with those other two. We don't have anything that can marry gravity to the other three. And because we lack that, we don't understand what happened in the first trillionth of a second of the Big Bang, and we don't understand what happens inside a black hole. We never will until we understand how gravity and quantum mechanics interact. So an idea that that ties together all four forces would be quantum gravity, and that would be one of the most massive steps forward in science that we could ever have.
Is that the same? Is that another way of saying the same thing about the unified field theory, and something that Einstein, at the time of his death, was perhaps the question that he wanted the answer to the most as well?
Yeah, it's the same idea as the grand unified theory. The field, the names get kind of weird. For a lot of people, the grand unified theory is just the three together, and then a fourth one would be a theory of everything. And depending on who you ask, the grand unified theory is all four. But, you know, any field you get into, the jargon is going to get weird.
I see that. I suppose we're going to have to wrap up in a few minutes. Maybe Constance can tell us we started a few minutes late, but and maybe we have a few more minutes to chat, or few more minutes. So do you work underground? Like, how often are you do? So you're an experimentalist, right? So some physicists are theorists and some are experimentalists, and you must be an experimentalist, right?
Yeah, I originally trained as a theorist, but there's something so fulfilling about running an experiment and basically plucking information out of the universe that I find really fulfilling. So yeah, and I'm an experimentalist now.
So you go to work and you go down in a cage a mile underground, and well, what's your day like?
Yeah, you get up earlier than is healthy. You get on that cage and travel for 12 minutes and 37 seconds, not that I've timed it, all the way to the 4850 level. You either catch a train ride or you hoof it over to the Casper experiment, which is about 1 kilometer from where you get off of the cage. And then your day is filled with turning wrenches, trying to figure out vacuum pumps, working on electronics, reprogramming computers, working on software. You have to bridge this large gap of, or I'm sorry, you have to run this large range of skills to get it to work, because any given day you could be whacking something with a hammer or working on something with a magnifying glass and tweezers, or programming a computer, designing a circuit. It's a large range.
It's a pretty interesting. I did go underground in Sudbury at Snow Lab, and it was a fascinating, what an interesting workplace, a mile into the earth. And, you know, maybe we could leave you. I love mind-blowing ideas like the fact that these atoms were actually forged in stars, except the hydrogen, but that's just a remnant of the Big Bang, which in some ways is even cooler. But there's from my notes from when we first spoke, I have a sentence and with no context, so I don't know what led up to it, but I think this is what it is. There you are, a mile underground, and the point of that is for the sake of the sensitivity of the instruments, to shield out everything else, every other kind of radiation, so that you could look for this faint signal. But it turns out, the sentence I have written down is, "We are radioactive." I think that's something you said, and I think this was the topic, right?
Yeah. We go underground specifically to get away from all these signals that are also put off by radioactive anything. And it turns out the human body is fantastically radioactive. We have uranium and thorium, and mostly we have potassium in our bodies, as well as, isotopes of calcium and carbon that are radioactive. We're this close from glowing in the dark. So when we come underground, we have to shield the experiments from the environment, and we can do that with the rock overhead, but then we also have to shield it from us. which is weird to be the radioactive source in a room.
Yeah, you're trying to do your experiment and you're messing it up. You're radiating. Usually saying someone is radiant is sort of a compliment. But so throughout this week, in the same time slot, tomorrow we'll have an interview about neutrinos, and then on Thursday it'll be dark matter, and then on Friday, the end of the universe. So from the Big Bang to the end of the universe, and then on Saturday I'm performing. And you know what? Speaking of stellar nucleosynthesis, my performance is entitled Brian Malow, Just Add Gravity. And what that comes from is thinking that, like, after the Big Bang, you have this expanding universe filled with mostly hydrogen and a little bit of impurities, helium. And maybe there's a teeny bit of lithium too. Is that maybe? But that would have been, as you said, a very boring universe, but just add gravity. That scenario. And the concept.
Absolutely. Through these incredibly simple ideas combined, you know, a universe filled with hydrogen and one attractive force, you get the complexity that we see in the universe today.
You get stars, and then the stars take those simple building blocks and make all these others. Pretty incredible.
Yeah, absolutely.
So, yeah. So is there anything any resources or anywhere that people could find you online, or anything about the lab, anything you want to mention before we say goodbye?
Well, absolutely. Please visit sanfordlab.org for a lot of the information on the experiments and how we run day to day. And I'll ask the Neutrino Day team here to put my email address out there. I'd love to answer questions people have, and maybe we'll have it go through the communications department. We can set something like that up. But yes, absolutely. Contact us. We love to answer questions.
You've done a great job answering my questions. I really appreciate it. Mark Hanhardt from the Sanford Lab. And Constance, I didn't know, did you want to
I'm back.
Say anything? What's coming up? Yeah.
Yes.
What's coming up next?
All right. Well, Brian, thank you so much. And Mark,
Sure.
thank you.
Thank
This
you.
has been great. We do have some follow-up activities that I would like to share with you. So at noon today, we have, what is the name of it? It's called There's Gold in Them Thar Hills, which is being led by Peggy Norris, who's with our education and outreach team. Also, we still have the anytime activities. We want you all to participate in those. You can go to our website, www.neutrinoday.com. You'll want to participate in the scavenger hunt, the investigator notebooks, if you want to win prizes. Other highlights from today. Tonight, we have artist in residence Gina Gibson, who spent a year with us at Sanford Lab and has created some wonderful pieces of art. And she's going to do a virtual exhibit tonight and talk to you a little bit about her experiences. Also, we're going to have
Have you ever had a comedian spend a year at the Sanford Lab?
No, although I work with some...
Just asking for a friend.
I work with some people who think they're comedians, and I'm sitting
No one in particular here.
I'm sitting across from one right now.
Hey, by the way,
Yes.
on Friday, after my interview with Katie Mack, what am I going to be doing with Mark?
Okay.
We have an event. We have another event together.
If you would stop interrupting me, Brian, this is my part of the show now. I was just going to say, remember to submit your bad science jokes, because we're going to have a bad science joke face-off this week, Friday, after Brian's last discussion with Katie Mack. Also, tomorrow morning, I'm going to be visiting with Erica Caden from Snow Lab. She said she knows you, Brian.
Yep.
And she's going to tell us a little bit about the connections between Sanford Lab and Snow Lab, and just a little bit of a hint there. It has something to do with Ray Davis and solar neutrinos and Nobel Prizes. Just
Interesting.
check in for that. And then,
You know, can I just say, can I interrupt you again? In fact, I'm not asking permission. Apparently, I'm just doing it. I'm interrupting to ask you if I can interrupt. But when people send in bad science jokes, I'm going to make a prediction. They better not be any of my jokes. People sending
Aaron,
in as
could you
examples
please
of
remove
bad.
my jokes that I submitted? They were Brian's. I'm just kidding, Brian. I have one that's not science related that I might submit, or I could just tell it right now. It was actually created
Sure.
by my daughter when she was 5 years old.
Yeah.
Okay, I'm going to direct this to you, Brian. If you don't get it, we'll give Mark a shot. Why did the cow cross the road?
Why?
Takers? It was the chicken's day off.
Ah.
Fabulous. Not physics, and she was 5. Shout out Mikhail Walter Campbell. All right, so finally, tomorrow at 10 o'clock, we will have Brian back again with Ryan Patterson, a Dune scientist. You can ask more questions about Dune and neutrinos and so on. Now I just want to give some special thanks out there. We've had a lot of people who support us, including sponsors. So a big thank you to our major corporate sponsors, Black Hills Energy and RCS Construction. Also, Monument Health, South Dakota School of Mines and Technology, Black Hills State University, and South Dakota Public Broadcasting. Our in-kind sponsors are Howgo Broadcasting, Home Slice Media Group, KEVN Black Hills Fox, Kelloland, Simpsons Printing, Mile Up Marketing, and Allied Arts Council. Finally, I need to say a big thank you to our surf team and all of our partners who put activities on our site. It has been an amazing turnout this year. We're so grateful to everyone for being a part of Neutrino Day. It's just overwhelming almost. We so appreciate it. But I have to really thank my Neutrino Day planning committee because this group did a great job of making sure things could happen this year. Matt Kapist, our creative service developer, and Nick Hubbard are kind of behind the scenes. They're making sure all the cameras and the audio is working. Erin Broberg, our communications specialist, who is our social media guru. She's just been amazing on this. And she's been doing all the writing about Neutrino Day. Cody Klein, our fabulous intern from Black Hills State University. He was on camera with me a little earlier today. The first experience, I thought he did a great job. Good work. Mandy Knight, our administrative services manager, helps us with logistics. Natasha Wheeler does volunteer coordination. Not a whole lot of that this year, but she's been a tremendous help in other ways. Deb Wolf, Education and Outreach Director. Becky Bundy, our Education and Outreach Education Specialist. And Jason Rosedal with our Environmental Safety and Health Program. Everybody worked together to make things happen and to make sure everybody stayed safe during the pandemic and, that we all followed protocols. So thank you all for joining us, and I'll see you back here at 6 o'clock tonight. Thank you so much, Brian. Thank you so much, Mark.
Yeah.
I'm really excited about the rest of this week.
Me too.
Thanks.
Thank you.